brief introduction of Sandipan ji. Dr. Sandipan Nalawade ji is working as Assistant Professor, Department of Physics in Guru Nanak Khalsa College, Mumbai. Dr. Sandipan ji has earned his MSc from Savitribai Pune University, which was formerly was University of Pune, and his PhD from Defence Institute of Advanced Technology, Pune. His research interest lies into optical fiber sensors, and in teaching field, he is teaching in mechanics, optics, and electrodynamics. Today is going to speak on the speciality of optic fibers, a step ahead towards Viksit Bharat. Over to you from your Dr. Sandipan.
Okay, and why I chose this topic, because optical fibers have many applications. You must have heard about optical fiber has a application in optical communication, and I assume that is it visible to all these PPTs?
Yes, sir. Yes, sir. It is visible.
Yes,
okay, thank you. And I am audible, right?
Yeah.
Yeah, thank you. So what I'm assuming a little bit about total interreflection, that is light is guiding through the fiber, but still I just cover the basics of optical fiber, and we'll see for communication. Already we know that optical fiber is used for optical communication, and most important thing is why this communication is so fast, because light has a speed 3 lakhs kilometer per second, and if you sending a light in a optical fiber, that is the core of the optical fiber, is 2 lakhs kilometer per second. So that's why whole world is connected with optical fiber communication. That is the one thing. So I will cover in this whole lecture some basics. Then we'll see we are not bending towards the optical fiber communication, but we'll see how optical fiber used as a sensor and its different techniques. Then, as I choose this topic, specialty optical fibers, or you can say specialty of optical fiber sensors, okay, in different applications. So we'll see what types of new optical fibers enters in market and how people are using, even industries also. We'll see the applications. Also, we'll touch the recent advances, what people did in these 5-6 years. Okay. So first of all, as you know that the total internal reflection phenomena is invented Tandal, I think before 20-30 years this cow paper comes into the market, into the research journals actually. So it's a basic phenomena that if you send a light through the water flow and it follows that water path only. So that is the basic. But if you see the Snell's law, okay, if you are sending light from rarer to denser, it is bending towards the normal. But if you sending in a reverse way, that is denser to rarer, the refracted ray bending away from the normal. So cow has got the Nobel Prize because of this paper, 1966 paper. Though it's a half award, but this optical fiber is very useful in communication nowadays, and that's why you communicate video, audio, or in all kinds of communication we did by using optical fibers. So what are the advantages actually? Before I start, I just tell you the basics of fiber optic cable. It's just a glass wire actually. It's made up of silica and it's only 125 micron in diameter. So it's a non-electrical first of all, because no any electrons flowing through that optical fiber. It's an optical waveguide actually. Okay, without contact, without these things, we can use as a sensor also. It is useful in a remote area or in a radiation area, or hazardous area, you can use these fibers because it's made up of glass. It has a very small size. I already told you that is core and cladding. Total up to the cladding diameter is 125 micron only. And its weight is very less. Okay, installation is very easy. Here is no electrons in conduction, so there is no electromagnetic interference. Accuracy is very high because we are using light as a light matter interaction, we can say, or measurement is applying on that light actually. Okay, so it's in terms of its spectral measurement, it may be intensity, that is intensity measurement, and so on. So that we will see one by one. And there are so many advantages over electrical sensor or electromagnetic sensor of optical fiber. So this is a basic of optical communication. We will not go into these. Most important thing is actually there are 3 communication windows, or you can say optical fiber. Okay, you are sending a light through the optical fiber and it has 3 communication windows. Communication windows in the sense that in that windows optical power loss is very less. So generally people are using 850 nanometer, 1310 nanometer and 1550 nanometer. So you can see attenuation versus wavelength. You can see at 1550 nanometer, okay, in this range actually here, okay, around 15 nanometer. Actually, why 15 nanometer? Because lasers, erbium doped fiber lasers available in this region actually. But all these communication windows lies in the IR range, infrared range. So generally in communication, people are using 15 nanometer window, communication window. So what is a fiber? Actually, it consists of core, which has a more refractive index than the clad, okay, and light is guiding through the higher refractive index. That is called as the total internal reflection. And in communication, okay, why communication is so famous and so commercial? Because of semiconductor laser diode as well as semiconductor photodiodes. That is a main thing actually in this. So this is a construction of what is the optical optical fiber looks like actually. It's a cylindrical glass wire. Okay, it consists of core, cladding, and jacket. Jacket for just, it's a glass, so it's very brittle. So just for the protection, we can say, okay, we are using jacket or some insulating material, plastic, something like that, or some polymer they are putting actually, that jacket consists of. So up to the clad, and light is guiding through the core only. And let me tell you here that core has, for a single mode fiber, core diameter is 5 to 10 micrometer only, and for a multi-mode fiber it is 50 to 100 micrometers. Okay, so if you compare with human hair, okay, its diameter just double the diameter of human hair. You can imagine light is traveling through the core at 2 lakh kilometers per second in a core, and there is very less loss actually. Very low loss actually. So because of small size, it is opening a new these things. We can easily use this fiber as a sensor. So we'll see the technique actually in a next. Okay, that we know, I think, how total internal reflection takes place. Okay, it's a simple Snell's law actually. N1 sin theta 1 is equal to N2 sin theta 2, where N1 and N2 are the refractive indices of material 1 and material 2, and theta 1 and theta 2 are the angles, incidence angle and refraction angle. As I told you that when you are sending a light from denser to rarer medium, then what is happening? Okay, refracted ray bends away from the normal. I will show you here. We can see in a first diagram, okay, I'm sending a light from denser medium, that has a more refractive index, okay, and cladding has a little less refractive index. So what is happening? Okay, in a second diagram, okay, the incidence angle is called as a critical angle. Why? Because the refracted ray is along the boundary of two media, and if you still increasing the incident angle from the denser side, what is happening here? The whole refracted ray, okay, is reflected inside the dense material. You can see here, okay, you can see here how laser is, okay, guiding by on the basis of total inter-reflection phenomena. Now these are the technical terms actually, how fiber light couples, how much light is coupling through the core. If it's single mode fiber, it's very difficult to couple a light through the core of the fiber, because the core diameter of the single mode fiber is only 5 to 10 micron. But if it is a multi-mode fiber, it's little bit easy. But if you see the numerical aperture, that is the acceptance of light in the core, that is, it depends on the square root of n1 square, matlab n core square minus n clad square actually. That is a numerical aperture actually. Okay, we'll not talk about modes and all those things because it's related to the communication, how modal dispersion, okay, you can reduce by using graded index fiber. Okay, that we will skip here. Actual commercially available, there are many protection layers on the fiber. Okay, so why optical fiber sensors? So first of all, signal is light signal, actually electromagnetic wave, and it's very small in size, so you can easily you can stick or embed, or you can use this sensor in a small area. That is one thing. Okay, we are using dielectric material. Glass is a dielectric material, so there is no any electrical interference, so there is no kind of voltage or current there, no power at all, electrical power actually. There is no electromagnetic interference, as I told you. Okay, point as well as distribution, you can easily find out the point to point or distributed point sensing actually. For example, in a civil structure, for example, you want vertical as well as horizontal stress. Okay, so you can easily find out by using distributed sensors, or you can see the distribution of stress in that slab or something like that. Okay, it has a very wide dynamic range, and multiplexing also possible because you can use different wavelengths for different sensors. So multiplexing also possible with the different techniques. these many parameters you can sense by using optical fiber sensor. Okay, temperature, pressure, flow, liquid level, displacement, vibration, and so on. Many things, chemical, physical, okay, or mechanical, you can acoustical, so you can sense by using optical fibers. So this is a simple basic principle actually. At one end you have a source that may be a laser diode, okay, or light emitting diode also. If it is not required laser diode, okay, you can use a light emitting diode also. There is a fiber, and at the output there is a detector. Now just a simple question: if I'm sending a light, okay, through the fiber, and if I'm bending, what will happen? Is there any change at the output intensity? Just I'm asking for if you're bending the fiber, that is fiber cable, is there any change at the output intensity? Because if you bend, the critical angle may change, and there will be loss of some rays or modes, we can say, into the cladding. Okay, light is no more guiding through the core. So just by bending, you can use as a pressure sensor. Just by bending, you can use a load sensor. But if you want more sensitive that sensor, okay, so you may require different design or a mechanism to detect that measurement actually. So there is a change or manipulation or change because of measurement in intensity of light, maybe phase, its electromagnetic waves, polarization, and wavelength. Okay, these are the basic things that may change at the output because of measurement. So as I told you that it may be intensity based sensor, that is light intensity, obviously phase of electromagnetic wave. Actually it's related to the interference and all those things. Interference, or we can say general interference, Mach-Zehnder or Michelson interferometer by using optical fiber cables. Polarization, polarized light you can use, and you can see the rotation because of any measurement at the output, and either wavelength, that is frequency, you can take it. So this is again a basic, and if you increase or you want to just take out the unwanted signal, so you require some electronic processing, or if you want to measure some dynamic or real-time data, so you use that type of electronic instruments to measure that measurement. So this is first one, but little bit complex actually. This is a Michelson interferometer. As you know that even in a space actually you are sending two laser beams at 90-degree angle in Michelson interferometer, and you are observing the interference phenomena, that is rings actually, interference rings. Okay, if you move one of the mirror, okay, there is a change in interference pattern, you can see here. Okay, so instead of this mirror, okay, small change in a mirror, actually there is a big change in a interference pattern. So instead of this, like you must have, do you know the gravitational detector actually is a laser interferometry, and it's a Michelson interferometer, nothing else. There are two mirrors at two arms, and they are sending the light, and because of space shrink or expansion, okay, there is a fringe shift actually. But they have to avoid the all thermal and vibrational mechanical effects, any noise they should, then only they can detect the gravitational. So there also people are using, but they are using the laser beams in a space, in a vacuum maybe. Okay, but here we are using the two arms which are made of a fiber actually. This is a 3 dB coupler. 3 dB coupler in the sense that if you are sending 1 milliwatt of light to this from the source, it is divided into 0.5 milliwatt and 0.5 milliwatt. So either you can, means if there is a change or displacement of one of the mirror and one of the reference arm actually, so there is a change in the output that is at the detector. Or else if you have some pressure or some load or some strain in one arm, there is a change in the interference pattern. Okay, similarly here this is a Mach-Zehnder interferometer actually. So again, instead of these two mirrors, what we have used 3 dB coupler. Okay, what is happening here? Light is reflecting back from these two mirrors, and it is interfere here, and it is coming out at the detector actually. Similarly here, what is happening? Okay, two rays or two different electromagnetic waves, they are coming here, interfere at the second 3 dB coupler, and you will get an interference pattern here. So intensity versus wavelength, there are some peaks or dips, okay, as a function of lambda, that is the wavelength of this thing. Second one, that is that these are the based on the interferometer. Second thing that is commercially available, so that is called as a fiber Bragg grating. You must have heard that Bragg law, okay, but that in X-ray diffraction or something like that. So here this is the fiber cable actually, and if you have a periodic change of refractive index in core only, okay, there may be in a clad, but because our light is guiding through this core only. So what is happening if you are sending a broadband source through this fiber and there is a fiber Bragg grating, okay, what is happening? Okay, with the Bragg condition, that is a pitch as well as refractive index of N1 and N2 periodic. Okay, what is happening? One wavelength, one color, we can say, it is reflected back, and at the reflected spectrum you will have a peak. Here at the output in a transmission spectra you will have a deep. Okay, so what is happening if you apply some temperature, there is an expansion or there is a change in a refractive index. So what is happening? This deep or this peak, they are shifting either left or right. Okay, so that is the second type of fiber bracketing, which is very successful in commercially. Actually, it is very successful, and it is giving a point, we can say it's a wavelength, its length is less than 10 mm, that is 1 centimeter, 10 millimeter. Since it is best, actually you can either use bending type of these things. You can do a U shape, or you can have a one transmitted fiber and one reflected fiber, and there is a mirror. If there is a change, displacement of mirror in a receiving fiber, there is a change in intensity. There are number of intensity also. Polarization also, there are in a market, actually there are birefringent fibers, actually highly birefringent fiber. So they maintain a polarized light throughout the fiber, because along one axis there is a different refractive index than the perpendicular axis, actually. And wavelength and frequency, that is a spectral or interference base that I have shown here. There is Fabry-Pérot also and different interferometers also. So come to the specialty fibers. Actually nowadays, okay, instead of core and clad, if you have a material, only single material, because to change the refractive index of cladding or core, to have a refractive index of core is more higher than the refractive index of clad, people are doping actually in that material. But there is a new type of fiber that is called as a photonic crystal fiber. Okay, and the light is guiding through this fiber is based on the modified total inter-reflection. Let me tell you that these are the cross sections. Actually these are the cross sections, so you can see there are different types. Okay, but if in a cladding area you have a air hole throughout to 2 micron or something like that. Okay, so what is happening here? Okay, refractive index, effective refractive index of this cladding area is less than the solid air, actually. So what is happening? Light is guiding through this core only, with some losses obviously, okay, because of this. But this is made up of single material, so generally you have a temperature cross sensitivity that may be reduced, or there will be very less temperature sensitivity if you measuring the pressure or strain or stress, something like that. Okay, so these are the types of cross sections, actually different fibers. I will not go into the detail. And second thing is photonic band gap fiber. This is another one. Okay, and these fiber, our CGCRI Kolkata CSR lab, okay, they are manufacturing from 7 to 8 years these type of fibers. You have air holes throughout the fiber along the axis in the cladding area. Okay, not a photonic band gap fiber. In a photonic band gap fiber also, it is called as a low index guiding fibers. Okay, photonic band gap means if you see the butterfly, you can see particular color is reflecting. Why? It is because of photonic band gap. Okay, so here even in an air core, I'm telling air core that has a low refractive index than the solid glass. Okay, so even in an air core light may be guiding, but here the limitations, you can guide only a single wavelength or some discrete wavelengths, we can say you can guide, but loss is very less by using these photonic band gap fibers. So how you can manufacture this? So you have a stack of so many glass tubes, and if you are melting this at 1900 degrees Celsius, and if you are drying, you will have these type of fibers, that is photonic crystal fibers. Also it is called as a holy fiber or microstructured fibers. Okay, so it has many advantages actually. So first of all, we'll see what type of or what I have used these fibers for sensing applications. Okay, so this particular type of fiber actually used, which is purchased from the Denmark, is called as a polarization maintaining photonic crystal fiber. Why polarization maintaining? You can see here, and I have shown the cross section. This is a cross section of an optical fiber. Okay, you can see there are many holes actually of 2 micron, almost 2.2, and this big hole is 4.5 micron, and whole diameter of the fiber is 125 micron, and these things only up to 40 micron. This microstructuring or fully with solids only 40 micron. You can see here, okay, refractive index along this axis is less than the refractive index along this axis. So what is happening? If you are sending a polarization maintaining light, it will maintain throughout the fiber. Second thing, and very important, generally, especially you can say, we have used this or we propose this fiber for tsunami sensing also, theoretically. Okay, why? Because there is no temperature cross coupling by using polarization maintaining base sensing actually. So it's temperature insensitive actually. So as compared to other fibers, this fiber is very less temperature sensitive compared to other fibers, because there is no second material actually. There are combination of air holes and solid material in the cladding region, and there is a solid core actually at the center. Okay, so it's made up of single material. 30 times we have seen its birefringence and all those things. Okay, and its light is guided through the, I told you that it's modified total interreflection. Why modified? Because there is no second specific material as a cladding. Okay, now come to the why I choose this, the step ahead to the Viksit Bharat. Or do you know the Tejas, that is light combat aircraft actually? Okay, it is made up of composite material, mostly composite material. So its weight is very, very less and strength is very, very high. There are carbon composites as well as glass composites. Nowadays also in automobile industry also people are using composite materials. Okay, so in this actually Tejas is with the help of DRDO as well as Hindustan HAL, I think. Okay, they manufactured this aircraft. Okay, it has a very less weight and very high strength. It's totally manufactured in India. Okay, for Air Force, for Air Force actually, for defense applications. So in this, they have used so many optical fibers which are embedded in this, in the wings or structure of this aircraft actually. So there are pressure, temperature, or see all optical or oxygen sensor they have used actually. Okay, so we'll come to what is composite. Resin plus some carbon or glass composite. If you add it, it has a very high stiffness. Okay, it has a huge strength to weight ratio, and there are many things, no corrosion at all. So that's why people are using, instead of metals or alloys, they are using composite materials. And in DRDO, let me tell you, so many labs, they are manufacturing even bridges for army as well as bodies of civil structures, bodies of not civil structure, tanks and aircraft. They are using these materials. So there are huge applications of this composite in different areas. Okay, so first of all, how you are monitor the health of these materials, that is most important thing. Okay, fatigue or there is a damage or something like that. And if you compare the electrical versus optical fiber sensor, we already seen these advantages. Okay, so first of all, I use fiber Bragg grating actually. So there is a fiber Bragg grating, as I told you that there are periodic change in the refractive indices, and I just given some strain here. So there is a change in the spectrum. Here I have given the Bragg's law. Why ineffective? Because of after writing in the sense that you are encrypting or you are changing the refractive index periodically means with same pitch actually, and some particular wavelength is reflected back. So if you send some broadband source, okay, particular peak or particular wavelength is reflected back, and you can monitor here. If there is a change in a strain, what is happening actually? There is a change in a pitch. This is capital lambda. Okay, so there is a shift in the, you can see here, shift in the peak or deep actually. Similarly, I have used second technique. This is called as Sagnac interferometry actually. It's again a interferometric technique. It's simple, very simple. I use this PMPCF, that is polarization maintaining or high birefringent fiber in this Sagnac loop, and it's observed. You can see there is a transmission spectrum actually. How it, at some wavelength there are deeps and some wavelength there are peaks. So by using this transmission, these things you can see at different. If you apply any measurement actually on this, what is happening actually? There is a shift in the deeps or peaks. Generally, we are looking at sharp deeps actually, so that you will have a more accuracy. So you can see here in my research work, I have embedded. This is a carbon composite actually. I embedded 3-4 sensors actually. You can see here I have used. You can see here fiber. Is it visible? Fiber, yeah. This is a fiber actually. These are so many glass fibers. It's not visible because it's transparent. Okay, you can see from this connector actually, there are some fibers actually. So many, for example, polar photonic crystal fiber I have embedded in this as well as I've embedded the fiber crack grating. I've embedded the polarization maintaining fiber, but I use the technique that is a second loop interferometer, and I use some other birefringent fiber, which is made of two different materials. That is panda fiber or panda fiber actually, which is available in the market. And I have compared all these. So you can see, first of all, I took the axial strain as well as cantilever strain, these things. So this is a optical spectrum analyzer. Here I just hold the fiber, and at one end I just axially longitudinally I'm stretching it. So, and then I have monitored the change in the shift actually, in the dips, that the interference pattern actually. Similarly here cantilever I just bend, because so many structures, it looks like a cantilever also at so many places. As well as I have used for temperature measurement, just to compare the ordinary or conventional fibers or conventional sensors with this polarization maintaining fiber. You can easily see, embedded means inside that surface bonded means just I stick with the resin, that fiber on the composite material only itself. You can see here, in embedded you will get good sensitivity as compared to fiber Bragg grating actually. Here also, but in a negative, for a strain, fiber Bragg grating has a more sensitivity than the PMPCF. So you can say that for a strain, for a surface bonded, there is less sensitivity as compared to the embedded one. So it's better to have. Why it's possible to embed the fiber? Because its diameter is 125 micron. With coating also it's 250 micrometer only. So we have compared it, the surface bonded, then non-embedded and embedded, these three, PMPCF and FBG, that is polarization maintaining fiber. Also you can see, as compared to the FBG, there is very less sensitivity, spectral sensitivity can say, as compared to the FBG. So it has a very less temperature sensitivity also. So you can say temperature insensitive strain sensor by using, and I have compared these PMPCF with the fiber Bragg grating, that is polarization maintaining photonic crystal fiber with the fiber Bragg grating sensor. This is commercially available actually. So many people now, different types of PCF, that is photonic crystal fiber, they are using for different applications. Similarly temperature you can see here, PMPCF has 4.68 and it has 7.6 picometer actually per degree Celsius. So half almost, you can say, for surface bonded. For embedded it is 3 times less. Different things, because for structural monitoring you have to choose whether you have to embed this fiber or this fiber sensor, or you can just stick or on the surface. And I have compared with the unembedded, means non-embedded sensor actually. So conclusion is, this new type of photonic crystal fiber or microstructure fiber, it has a very low temperature sensitivity. So there is no cross sensitivity or cross coupling, you can say, with any other parameter. Similarly, second thing, I use for a vibration, that dynamic thing actually, the same fiber for a dynamic. Then I have used, again, embedded this fiber into the glass composite, and I've given, this is a schematic diagram, I have given some vibration at one end of the cantilever, and there is a change here. I have used the polarization based principle to measure the change in at the output signal actually. There is analyzer, so there is a change in a polarization. You can easily, there is a change in intensity at the output, and you will have a signal conditioning unit. And I have used the LabVIEW. I use the LabVIEW with some DAC card actually for acquire the signal. So you can see here, these are the basic principles actually, how intensity as well as phase changing with X and Y mode, or vertical or horizontal mode, you can say. You can see these are the real time actually signals measure. First one is in a time domain, and second one is in a frequency domain. So in a LabVIEW it's possible to convert that into Fourier transform, that time domain signal. So you can see here, this is a time and this is amplitude axis. And obviously for mechanically I have given 1 Hertz vibration to that sensor, and easily you can see here at the peak or frequency at 1 Hertz. Similarly, same repeated for a 20 Hertz, 50 hertz, but you can see at a 50 hertz there is a huge noise actually as 50 hertz. So we have to see the range of the vibration sensor. That is very important, this particular vibration sensor. Then again, there are different types of excitations actually for that vibration. Means I've given different types of, like in electronic signal you have a triangular, square, as well as sinusoidal. So there is a different types of, you can give excitation, different excitations actually, mechanical excitations obviously, not electronic. Okay, so again the same thing I have repeated. Again, a square wave excitation, you can see in a square wave excitation there are some harmonics I have observed. Okay, so for vibration sensor I have used this sensor. And why I use for vibration sensor? Because it's less temperature sensitivity. So in a harsh environment you can use this fiber sensor. Okay, in a harsh environment also. Similarly, delamination detection or some fatigue there, so I use, okay, I made two samples. In a one sample it's totally healthy sample, and in another sample I have just inserted some other material at these places, and I just compared these. Is a big little bit big, 1 meter or something like that in the length. And also here you can see there is strain gauge actually to monitor the vibration or load actually. So given a free vibrations, you can, again I did the same thing for this, but not in a cantilever. I have given the vibration at the center. Okay, or just I given a simple just a damping and left it. So I got this time domain signal, and this is a frequency domain signal. For different lengths I just see different things. So this compared with the natural, if you are damping freely, obviously that material is vibrating at a natural frequency. And just I wanted to just tell you that, okay, any civil structure, if it is vibrating at a natural frequency, there is a chance to crack that structure. Okay, because that for at resonance, actually resonance happens, and amplitude is very high, so there is a chance to break or damage that structure, or any even vehicle also, if it is vibrating at that frequency, natural frequency. So here these are the funded project from DRDO actually we have completed. Okay, as sir has mentioned that these fiber sensors we have used for magnetic field detection. Before starting this, let me tell you that there are air holes, okay, in the fiber, and if you have some thermo-optic liquid or chemical or some other material, any other material that is because of that measurement, it's changing its refractive index or some change in, so that material you can just insert in that air holes, so that fiber may be more sensitive to that measurement. So Fe3O4, that is a magnetic nanofluid actually we have inserted into these holes, and we have applied the magnetic field. This is a setup actually. Okay, and again a same technique, polarization based technique we have used. Okay, this is a first linear polarizer to polarize the light, then send it, couple it into the fiber, and here the solenoid. This is a main fiber sensor, that is a PMPCF filled with magnetic material, we can say, or magnetic fluid, you can say. And at the output there is a linear polarizer. Actually you can say this is an analyzer, analyzed to the polarized light, and at the detector, that is an optical spectrum analyzer. And you can see here, okay, you can see first of all, with filled and unfilled, there is a huge difference between the two dips actually. Shift, you can see there are so many dips comes into the picture without fill. Here only two dips actually, and the difference between two are, okay, deep to deep, there is a big change actually. This interference pattern get expanded actually. Okay, so at different magnetic fields we have seen the pattern, and you can easily see there is a big change or big shift at the interference pattern. So these are the graphs of sensitivity. It comes out to be point in a negative, means it's a negative response actually. So it's 0.043. No, not at all. It's so the exponential decay actually. So per millitesla. Okay, 0.15 as well as 0.24 for different these things actually. Different concentration of magnetic fluid. So because of these air holes, it opens a new branch actually. You can either insert a nanofluid magnetic fluid or some other thermo-optic fluid into that, and you can make this sensor is more sensitive to that measurement actually. So recently actually before COVID, during COVID actually, IIT Mumbai, that is Powai, one of group, that is bio group, they have proposed this photonic crystal fiber for a COVID virus detection actually. There is a different technique actually that is called as a local local surface plasma resonance actually, and it's more sensitive to the chemicals, because refractive index, small change in a refractive index, it can detect easily. So COVID virus you can easily detect by using this. They have just proposed. Okay, so different types of chemicals as well as some biomolecules, DNA, RNA, this fiber is can use for this type of materials or this type of sensing by using photonic crystal fiber because of air holes. As I told you, that is what here. Okay, it has a huge applications in sensing actually, and two parameters you can easily monitor by using this PCF sensor because it's made up of single material. There are different material they have manufactured with different material also. That depends on what type of application do you have. Like if you want to write a fiber crack rating in a piece of photonic crystal fiber, so you need to dope that fiber with a germanium so that you can easily write the fiber crack rating. Otherwise it could have impossible to write the fiber crack rating into that. So these are the applications, these are the references. And Rajesh sir as well as Bhushan sir, thank you for giving me opportunity to share my knowledge as well as research with you people, as well as I thankful to the Arvind sir and my colleagues Jignesh sir, okay, to propose this. So thank you very much. If you have any questions. Hello.
You are not talking about anything about the fiber optic gyro.
Gyro, sir, I have not worked actually, but gyro you can use, but I have not used in my research field, as well as I have not have much knowledge actually about that actually. Yeah, there are fiber optic gyros also. There are many optical fiber sensors, many. If you monitor the polarized light, okay, because there are conventional highly birefringent fiber also, and they are made up of different materials. So they may have along one axis they may have a more refractive index as compared to other one, and it has a more thermo-optic coefficient as compared to the air as well as this. These are the made of single material only with air holes. So that's why it's less sensitive as compared to the conventional polarization maintaining fibers. And its light is guided because of modified total interference, in the sense the effective refractive index of this cladding region is less than the solid core, because light is guiding through this only, sir, solid core only. There are losses initially, but once it is guided through the solid core, it is guided.
Slides panel you had shown, there was a sensitivity of the various fibers. One was negative, all were positive sensitivity, one was negative. I didn't get it. Like what exactly happens there? I didn't know. Like one had.
What is actually happening? So it may be because of, sir, negative, or it depends on the technique, what technique we are using, or what parameter of light actually, or property of light you are measuring. That is the most important here. So what technique you are using, first thing, and second, what parameter, what technique, and second thing is that I have observed that one, because it may be it is responding negatively, it may be a positively also. That depends on the other technique also. So it may possible have it's a thermo-optic or refractive index. Thermo-optic means the refractive index is changing, okay, because of measurement. It's in a inverse proportion.